Okay, so I'm going to go over really quickly what I'm expecting for you guys to do in the spectral analysis lab. Okay, so if you download the student handout, there's no instructions, there's no procedure. Essentially, what I'm trying to get you guys practice and experience doing is taking IR data, taking NMR data, and essentially producing the overall structure, right? So I give you overall 8 different structures, right, that have their IR spectrum, that have the NMR spectrum to analyze. And I want you to take all of that data and I want you to tell me what the overall structure of the compound is, okay? So what I'm going to do is with the first structure, I'm going to walk you through this. I'm going to tell you exactly what I'm expecting for each one, okay? And so I'm also going to try to explain what you're seeing in each of these individual spectral datas, okay? All right, so note what we have given you here is we have given you for each compound the molecular formula. All right, so the molecular formula is listed up top. We have given you the IR spectrum. Right, so ideally you've watched all the videos dealing with IR spectroscopy as well as NMR spectroscopy, and you know that an IR spectrum is read as percent transmittance as a function of wave number. And so we've given you the IR spectrum for the compound. We've also given you probably the most important piece of information, the Proton Nmr spectrum, which is down here. And so note that in the Proton Nmr, we're reading chemical shift on the bottom. Again, we don't show you the peak for TMS, but TMS defines what 0 parts per million is. And that's been done already by the instrument, so you don't see a peak for TMS. And then we've also given you the carbon-13 data. So this is the carbon-13 NMR data down here. And we've also given you mass spec data for the compound, okay? So you're not going to actually see the mass spectrum, but instead we'll just get the numbers, kind of like what they do in the textbook. Now, there are going to be things, or there are going to be parts of this that are much more informative and much more indicative of the overall structure than others, right? So things that you need to focus on for this lab are the IR spectrum, as well as the Proton Nmr spectrum, as well as the molecular formula. Other things that are not super important are going to be the mass spec data as well as the carbon-13. I'm going to hopefully explain why those may or may not be important as we walk through this first one. Okay, so when I'm given a molecular formula of a compound and I'm given its spectral data, right, the first thing that I tell you guys to do in the lecture is to calculate the HDI, right? So HDI is a measure of unsaturation in the molecule, right? So what we're looking for here with HDI is everything single bonds, or do we have a double bond, right? Or do we have a ring, or do we have a triple bond, etc. Okay. So in the lecture, I give you the equation or formula to use for HDI. And again, HDI stands for hydrogen deficiency index. And so what that is going to be 1/2 of 2 times the number of carbon atoms in the formula, plus 2, minus or plus any nitrogens that we have, minus all of the hydrogens, and minus if we have any halogens, right? So these guys are halogens. And this is going to come from the overall molecular formula of the compound, right? So for our compound here, we only have carbon and we only have hydrogen. So essentially we can ignore the nitrogen, we can ignore the halogens because we don't have any of those guys in our compound. All right, so with that, to calculate the HDI here, I'm going to take 1/2, 2 times the number of carbons. There are 8 carbons. So 2 times 8, let's just get rid of the 2. This is 8. 2 times 8 is 16. I'm then going to add 2 to that, so plus 2. Again, there's no nitrogens. I'm going to subtract the number of hydrogens. There are 18 hydrogens. So 16 plus 2 minus 18 is 0. 1/2 of 0, or 1/2 of 0 is, yes, still 0, right? So an HDI equal to 0 tells us all single bonds are what make up the compound. There are no double bonds. There's no degrees of unsaturation. Everything is saturated. Right, so what if you had gotten a different HDI, right? So in slide 19 of the NMR lecture. So this is chapter 15 lecture. I go over kind of some of the ramifications behind what different HCIs mean, right? So if we had an HCI equal to 1, that would tell us that there is a double bond or a ring, right? If there was an HCI equal to 2, that would tell us that there's 2 double bonds or a double bond and a ring or 1 triple bond. There's a lot of different permutations of that for an HCI equal to 2. As we start to increase that HCI, there are a lot of different ways that we can get that, so it gets kind of confusing. The only other one that's kind of important for us is an HCI equal to 4 or greater. I guess I should say greater than 4. Greater than 4. This is usually indicative of the presence of an aromatic ring, and it will be important in a couple of the compounds that you guys solve, I think. I can't remember what these are made up of, but I'm pretty sure. Right, so again, what are we going to use HCI for, right? So again, we're trying to figure out the structure, right? Do we have double bonds in the compound? Is it a ring? Is there an aromatic ring? The one thing that's going to be important is knowing that if you have an HCI equal to 0, everything's saturated. We're only dealing with single bonds. If you have an HCI equal to 1, that's either a double bond or a ring. You don't really have to know HCI is equal to 2, but again, I would consult slide 19 in that chapter 15 lecture. But then also helpful to keep in mind, if you have an HCI greater than 4, it's probably an aromatic ring. Okay, so with that, that's the first one, right? So when we calculate HCI, it tells us, okay, what are we dealing with? Are we going to find a double bond somewhere? For this compound, no. Everything's going to be a single bond, so everything is fully saturated, okay? So then, after I calculate HCI, I'm going to go over to the IR spectrum, right? And so the big thing that we're going to take away from the IR spectrum for each compound is whether or not there is a functional group present. And that's really the only thing it's going to tell you. And I'm really trying to stress that. As a reminder, if you go through the lecture, there are 2 components to the IR spectrum. There is what we call the fingerprint region down here, and then there's the diagnostic region, which goes from about 1500 all the way up to 4000 wave numbers, right? If you guys assign stuff to this region, when I've told you that you can't really do much with the fingerprint region, I'm just going to count it wrong, right? So we're looking for functional groups. Functional groups are only going to be found in the diagnostic region out here, okay? And most importantly, for this compound, there are no functional groups, right? It's only carbon and hydrogen. There's no oxygen. We know there's no double bond. So the IR spectrum for this one is kind of worthless. It's not going to tell us anything, right? So for this one, I would say no functional groups present, and I would move on. Now, what if there is a functional group, right? So I've talked about, especially in the lecture, kind of really indicative functional groups in the IR spectrum. So one of those that you should be aware of is the OH stretch for the alcohol group, right? Another one is the carboxylic acid, right? So these guys give very broad signals due to hydrogen bonding. And again, it's going to be in a region that you would expect to find a hydrogen bound to something, right? Another one that's really indicative or very, I guess, indicative of a certain type of functional group is the carbonyl group, the carbon-oxygen double bond, right? So this can be in the form of an aldehyde, this can be in the form of a ketone, or this can be in the form of the carboxylic acid. So we would expect us to find this in the double bond region. Again, what's really, I guess, important about this one is that it gives a very, very, very intense signal, meaning a very deep trough, right? Not super broad, but very intense. And again, I go over reasons why you see that in the lecture, so be aware of that. Other things are going to be carbon-carbon double bond. This is not as deep. This is not as intense as the carbon-oxygen double bond. And again, there are reasons behind that that have to do with that bond. But then also maybe be aware of any type of carbon-hydrogen bonding that's found in the carbon-hydrogen region, right? So depending on whether or not these guys are sp3 hybridized, sp2, sp, we're going to get different signals in the area that you would expect to find a hydrogen bound to something. Right, so for this one, there is no oxygen, so there are none of these guys. There is no double bond, so nothing here. And we will find at about 2900, right, a peak that's due to, again, those carbon-hydrogen bonds to sp3 hybridized carbon, right? And so that's not going to help us do anything. It's not going to tell us anything about this compound, okay? So for this IR spectrum, there's not much to do. So we move on, okay? Okay, so then we'll move down to the Proton Nmr. And Proton Nmr is, especially for this guy, going to be the most important thing that's going to help us produce the structure for this compound given the molecular formula, okay? Now, there's a bunch of stuff that we can take away from the Proton Nmr, right? First thing is going to be the number of signals, right? So what is the number of signals telling us? It's telling us the number of chemically non-equivalent protons, of unique protons in the overall compound. The integration is really important. Integration, right? That's actually telling us for each signal how many protons are a result or responsible for that signal, how many H give rise to that signal. And then really the most important thing is the splitting pattern. So this is why I stress going through all of the Proton Nmr lecture, or at least understanding splitting, right? Spin-spin coupling and why we get these various splitting patterns. Because this thing is actually going to be the thing that tells us the most about who's nearby each signal, right? So who is nearby. And then if there were a lot of different electron withdrawing groups or anything like that, the actual chemical shift would tell us a lot too. But for this one, we don't really have any electron withdrawing groups. There's no oxygens, there's no chlorines or anything like that. So chemical shift tells us, for each signal, is there an electron withdrawing group, or what type of protons are giving rise to that signal. And so it's not as important as the splitting pattern or the integration, but it's also there to keep in mind. So for chemical shift, especially in these early ones, just as a reminder, methyl protons, we can expect them at about 0.9 part per million. And again, you're saying, well, where are you getting this data? Watch the lecture videos. Methylene protons, so those CH2s, we can expect those at about 1.2 parts per million. And then methine protons, which are just the carbon bound to something else, so CH3, these protons, we can expect these guys at about 1.7 parts per million. Okay, so now what are we going to do with that? All right, so if you do watch the spin-spin coupling portion of the NMR lecture, you know that I go over a couple of very characteristic splitting patterns that are very indicative of certain structural features in a compound, okay? One of those, which is really indicative, is a singlet, right? So a singlet that integrates to 9 protons, right? And so in each of these patterns, or in each of these NMR spectrums, they're giving you the integration pattern, right? So they're telling you this is a signal, it integrates to 9 protons. There's a signal here that integrates to 6 protons. There is a signal here that integrates to 2 protons. And then there is a signal here, which is very small. It's small because the integral is so small. It's only 1 proton that's giving rise to that signal. But what they've done here is they've taken that and they've zoomed in, or they've blown that up, right? So they're showing us what that signal actually looks like if we were to zoom in, okay? Okay, so that's number 1. This first signal, which shows up at about 0.9 part per million, right? It integrates to 9 protons, and most importantly, it is just 1 peak, right? It is a singlet. And so a singlet that integrates to 9 protons is 100% of the time, almost always, a tert-butyl group, right? Because essentially what it's saying is we've got 9 protons, they're all chemically equivalent, they're all giving rise to the same signal, and they are not being split by anybody nearby, right? Because again, equivalent protons can't split each other. They can only be split by non-equivalent protons, right? So a singlet that integrates to 9 protons is usually this guy. So again, if I say torpedo and you don't know what I'm talking about, I would go back to the alkane chapter where I talk about various common alkane structures and what their name is. So this is a torpedo group. Nope. And again, the protons that are giving rise to these signals are these guys. We have 3, 6, 9. They're all equivalent, right? And again, if there was going to be any type of splitting, they would have to be 2 to 3 sigma bonds away from a non-equivalent proton, right? And if we went ahead and, let's say, draw these guys in so that we can count sigma bonds. If we draw these guys in, we have 1, 2, 3, right? If there were hydrogens here, then that would be 4 sigma bonds away. There aren't, I mean, there may be hydrogens there, but even if there were, these guys are not going to be split by them. So because of that, we have n plus 1 equals 0 plus 1, which gives us a singlet. Again, that n plus 1 rule is n is the number of non-equivalent protons nearby. There are 0 here, so our overall signal for these guys is a singlet. And I'm going to go ahead and get rid of this. Make it back to this. And then we'll highlight this guy. Right? So that's number 1. That's a piece. Right? And with all of this stuff, what I'm trying to do here is I'm trying to make pieces that I'm then going to stitch together to make sense of the rest of the spectrum. Okay? Now, what's nice about a torpedo group is that it essentially terminates a molecule, right? So one of our ends is this thing because this can't go anywhere else. Nobody else can make more bonds, so this is going to be one end of our molecule. Okay? All right, so now that's one. Also important to note, with this torpedo group, we have accounted for We've accounted for 1, 2, 3, 4 carbons. We had 8 to get rid of originally, and we've accounted for 9 hydrogens. We had 18 to get rid of, right? So now we still have 3 carbons and 9 hydrogens left in the overall, trying to figure out the overall structure. Okay, so then after that, another very canonical pattern in the Proton Nmr spectrum for a very specific type of structural feature was what we find here. So we have a signal here that is kind of being obscured by that 9 proton singlet, right? This is underneath here, this essentially is a doublet, right? And that second part of the doublet is lying essentially like underneath that 9 proton singlet, so that's not why we can't see it. Most importantly, this is a doublet. And the reason why I know it's a doublet is because it integrates to 6 protons, right? Most importantly, though, too, is that we have this thing out here that's also telling me that this is a 6 proton doublet, right? Well, what is this? Well, this is a signal where we have a 1, 2, 3, 4, 5, 6, 7. This is a septet that integrates to 1. So this is only 1 proton that has 6 nearby neighbors, right? Because 6 plus 1 is 7, the septet, that's splitting its signal, okay? So again, another very canonical structural feature that would give rise to a doublet that integrates to 6 protons, a septet that integrates to 1, is that isopropyl overall structural feature, right? So isopropyl looks like this, CH3 with a hydrogen, okay? And essentially in this structure, there are 2 different sets of non-equivalent protons. These guys are equivalent, right? There is nothing different about them. These are equivalent. This guy, on the other hand, is non-equivalent. To them, it's by itself, right? So these guys is going to give rise to its own proton. So let's say we call this guy HC, HC, and HD. Okay, so then also with that, so this is isopropyl group. I'm going to go ahead, I'm going to erase this guy. It's still going to be there, but I want to go ahead to count sigma bonds. This guy is going to have a hydrogen. It's going to have a hydrogen. It's going to have a hydrogen. Okay, so again, these guys are equivalent. They cannot split each other, but they can be split by a nearby neighbor proton that is non-equivalent. Okay, that nearby neighbor though has to be 2 to 3 sigma bonds away. At this point in time, if we counted sigma bonds, we've got 1, 2, 3 here, right? So all 3 of these guys are within 3 sigma bonds of this proton, right? So for all 6 of these guys, pardon me, are within 3 sigma bonds of this guy. So for these guys, HC and that signal, right, they are going to give rise to an N+1, where N is equal to, that's 1 proton, 1 plus 1 equals 2, right? They're going to give rise to a doublet that integrates to 6 protons, which is what we find over here, right? Most importantly is this guy, which is just 1 proton, he's by himself, right? He is going to be split by 1, 2, 3, all of these 6 protons, right? So for this guy, for HD, N is equal to 6, so 6 plus 1 equals 7. This is going to be a septet that integrates to 1 proton, which is what we find right here. All right, so a doublet that integrates to 6 protons, the septet that integrates to 1 proton is almost, again, 100% of the time this isopropyl group. Now, this is also nice, right? Isopropyl also has to terminate a molecule. From this overall structure, we can't make any more bonds. So now we have essentially the 2 brackets, the 2 bookmarks, or not bookmarks, but yeah. Anyway, the 2 ends of the molecule. We have our terbutyl on one end, we have our isopropyl on the other. We've also accounted for pretty much all of the signals, right? So we've talked about the singlet that has 9 protons, the septet, or the doublet that has 6 protons, the septet that has 1. The only thing left to talk about is this guy, this 2 proton that integrates, or we integrate to 2 protons that, if you look at this, shows up as a doublet. And again, how do you know it's a doublet? Well, there's 2 peaks, right? It's a doublet. And you can see them, and they're very distinct. Sorry. So if we zoom in, or we freeze up. So we have a doublet here that integrates to 2 protons. Also, if we count our carbons and our hydrogens, at this point in time, we have accounted for 7 carbons with the 2 ends of our structure. We've accounted for 16 hydrogens. So we only have 1 more carbon and 2 hydrogens to go. Another important feature of this is that it does show up at 1.2 parts per million, right? And if we go over here, 1.2 is essentially a methylene group. Now, the only thing we have to be aware of is that splitting pattern, right? It's a doublet, so it can only be, so if N plus 1 equals 2, that's the doublet part, then N has to be 1. There can only be 1 nearby neighbor that is not equivalent to those 2 protons. And so if we know it's going to look like this, right, where these 2 are equivalent. And again, if we have a piece here, and if we have a piece here, the only way that we can stitch those together is we're going to put on our isopropyl group over here. So CH3, CH3. Let's move this. It's getting very mad at me. Okay, so we have this guy. We have our terbutyl. And then we have our isopropyl. Okay, so again, can we make sure and make everything fit the overall spectrum. This is it, right? We have how many carbons? We've got 1, 2, 3, 4, 5, 6, 7, 8. For hydrogens, we've got 18, so we're good there. Now, for this one, this is kind of like this last little bit. Does it fit, right, where we're at? We need 2 equivalent protons, right, because it integrates to 2. These guys are equivalent. That is only near 1 non-equivalent proton that can split its signal. If we count sigma bonds, we've got 1, 2, 3. So these guys would be split by this one, right? But then for everything else, it's too far away. We have 1, 2, let's say 3. And then if we're going out to one of those hydrogens, those guys would be 4 sigma bonds away. It's the same thing on the other side. So if we went 1, 2, 3 to go out, we would be 4 sigma bonds away, right? So these guys are not going to be split by any of these guys or these guys. It's only going to be split by this one. So that's it. It makes sense. It fits the pattern. And this is the overall structure for this compound, right? So there's a couple of different things that I want you to do, though, in showing me that you solved this structure. So what I'm going to do is I'm going to erase this because it just gets confusing. I'm going to erase this guy. And I'm going to say, okay, I'm going to call these guys, this signal, I'm going to call these guys HAs. I'm going to call this signal, these guys are going to be my HBs. I'm going to call this signal HC. And then this guy, this septet, I'm going to call this HD. And then I want you to go through and show me who is HA, right? So these guys were my HAs. I want you to show me who is HB, right? HB was these guys over here. So these are HBs. HC was these guys. And then HD was this lone one. And that's what I want to see. I want to see the structure, and I want to see which of these protons in the structure that you have solved correlate with which signal in the overall H1 NMR spectrum. Okay, so then there's other data, right? But it doesn't matter because this is the purpose. We wanted to know what is the structure. The structure essentially can almost 100% be derived from the H1 NMR spectrum unless there is like a functional group, and then you would need some help from the IR. We still give you carbon-13, so if that's helpful for you, feel free to use it. I don't think it's that helpful. And we give you mass spec data as well. If that's helpful for you, please use it. But really for mass spec, the only thing I've talked about in terms of mass spec is how to take this data and determine the molecular formula. The molecular formula is already being given to you, so you don't need to do that, right? There is some stuff, if you want to go through the book, where certain type of fragments give certain characteristic signals in the mass spec data. But again, I think most of that can come from the splitting pattern and the number of signals in the H1 NMR data, all right? Okay, so that's it. I would prefer these guys to be in in Lewis structure or drawn like this, as opposed to a bond line structure. You could also, to make it nice and easy, draw the bond line structure. So for this guy, it would be something like this. But I again need to see the protons, right? So that's why this is going to end up being better overall. Okay, so that's one, right? As you move through these, you're going to find that they're a lot easier because you're going to get more practice in dealing with a couple of these very characteristic patterns. So it's going to be easy to see certain things long term. But redraw these if you want to. You don't have to print this, right? If you just want to redraw the IR spectrum. Oh, that's one other thing I wanted to mention. For the IR, if there is a functional group, I want you to show me where it's at, and I want you to tell me specifically what functional group. Go on to the next one. We get an entire new compound. We get an entire new IR spectrum, entire new Proton Nmr spectrum. And so that's what I'm expecting for all 8 of these, right? So at the end of this, you guys will, right? So for example, in the second one, we don't have, again, if we're starting here, we're not looking at the fingerprint region, we don't have anything before 3,000. So I can almost 100% tell you There's no carbon-carbon double bond. There's no anything in here to tell us that. But there is this guy, and most importantly, there is an oxygen in this compound, right? So specifically, I look at this and I know that this is a broad signal. There is no carbon-oxygen double bond, right? We don't see that over here at all. It's not as broad as a carboxylic acid. So this has to be an alcohol, right? So that oxygen is coming from the alcohol, and that's also what I want to see in the IR spectrum. I want you to tell me this signal right here is because of this. And that's it. And that's what I expect for each one, right? So you go through this, you do the exact same thing. Note in the H1 NMR, we have a 6 proton doublet, and we have a 1 proton septet. So we've kind of gone over that. There are other signals, and now we're going to start to be able to do stuff with where they end up with respect to their chemical shift due to the fact that you do have an electron withdrawing group. You have a functional group present in this molecule. Okay, so go ahead. When you're done with these, take pictures of them and upload them to the quiz.